Good morning, my dear kids. In today's class, in the ray optics, we are going to discuss in the prism chapter prism. We'll discuss about the dispersion of white light. Then we'll go for the dispersion without deviation, then deviation without dispersion. There's one more theoretical topic of the prisms. After this, we'll go for the numericals. Okay, let me start the class. Okay, kids, like in the previous class, we had the discussion on the prisms. So there we brought the expression for the deviation. Let me take help of the same concept. So if you look at the basic idea, so if a monochromatic ray of light, let it be incident. This is a normal. So it will undergo some refraction here at first phase. Then so here let me introduce small angle prisms. What are the conditions for small angle prism? So what is a small angle? So if the angle somewhere, if it lies, then there's a basic necessity condition for small angle. If the angle of prism is somewhere, if it lies from 0 to 14 degrees, so then we'll usually call it as a small angle prism. We're in the same problem. Okay. Okay, this basically called as a small angle prism. So this particular angle, if it varies somewhere 0 to 14 degrees, then you have to call that a small angle. Okay, agreed? Then, what about the deviation suffered for this one? So this particular deviation I'm interested. Then we know this is I1, this angle is R1, this is R2, this I2. The net deviation is equal to I1 plus I2 minus A. And according to the Snell's law, sine I1 is equal to mu sine R1. As small angle prism, I1 is equal to mu R1. You take it on video. And similarly at other surface, sine mu sine R2. So mu R2 equal to I2. Substituting all these things, so deviation is equal to I1 is equal to mu R1, I2 equal to mu R2 minus A. So mu R1 what is R1 plus R2? That should be equal to A. So this will become mu minus 1. Okay, this expression for the deviation for small angle prism applicable only for small angled prisms. And how much is that small angle? I'm just mentioning it. Around 0 to 14 degrees, this is applicable. Okay, fine. So I think when you get it, this is 60 degrees. If the angle of prism 60 degrees, then this should not be used here. I'm making things very clear. Okay, fine. So then next again, if the prism, if it is hollow prism, then what conditions will come? I think I'm choosing like this. This is the hollow prism. Now the light, anything, how do hollow prism it is? This is what happens. So here, air, this is the glass, this is the air, and this is the glass. So here, so if a light passes through an hollow glass prism, then there won't be any deviation because this very thin, again the double refraction occurs. The refracted ray will be parallel to incident and we don't get any deviation, practically, which will be of no use here. So what I shown, this is a hollow glass prism. For hollow glass prism, there won't be deviation, which will be of no use for us. Hmm? That was a small angle prism, this hollow glass prism. So what is the conclusion? Hollow glass prism will not produce any deviation. Okay, small angle prism. So what is the deviation produced by it? Mu minus 1 into A. Then next we have hollow glass prism which will not produce any deviation. So next we'll go for the dispersion idea. I will move this diagram. So we'll discuss now the dispersion. What do you mean by dispersion now? So splitting up of light into its constituent colors is called as the dispersion of light. So what is the basic definition of it? This splitting up of light into its constituents colors is called as a dispersion. And we'll define spectrum. A band of colors obtained on screen. So there's like this we define the basic idea of a dispersion. When white light passes through a prism, it will undergo dispersion. So let me bring this one image here. Let me keep it here. Yeah. So when a white light passes through, I'm talking about the white light here. So when a white light, if I make it to pass through a prism, so let A be the angle of prism. Then, so the white light, what happen, will break up into its constituents. And this particular thing is called as a spectrum. I think you just take any prism and keep it in sunlight. So the sunlight after passing through the prism will break up into, will get a color band. This color band is called a spectrum. On the screen, if you place a screen, on the screen you can see the different colors in one specific order. So that particular band of colors is called as the spectrum here now. This particular phenomena is called as a dispersion. Okay, agreed? this particular thing. So why do that dispersion occurs and why the wallet will have more deviation than the red? So there's some theories what we have to uh, discuss here. So Cauchy's relation will help us. So according to Cauchy's relation, the refractive index of material mu of lambda is given by depends on the wavelength of this one, where A and B are Cauchy's constant. Hmm? Cauchy's constants and depends on material of prism. If you see for different materials, the value of A and B will be different. So usually we took the mu for a glass, how much it is around 1.5. Is it really 1.5? No, it is for the yellow color wavelength, it is 1.5. For different wavelength, the mu of material will be different. So there's a one basic condition which we have to accept and move forward. Where the what is mu? Mu is a refractive index. Lambda is wavelength. So like this, we define the Cauchy's relationship. So this is something very fundamental, which will help us a lot in studying the dispersion phenomena. Okay, now we know the Vibgyor, the spectrum, violet, indigo, blue, green, yellow, orange, red, lambda V, wavelength, wavelength of violet will be less than that of indigo. You know, wavelength of violet will be less than that of the indigo and that of the blue, no? Then look at this equation. How the refractive index and the wavelength. For lower wavelength, the mu will be more. So from here, I'll bring mu v greater than mu I greater than mu b. Okay, like this, the refractive index of the material for different wavelength will be related. So when I L violet wavelength, the material will offer more refractive index than compared to right here. Okay, now for small angle prism, what is the basic formula? The deviation equal to mu minus 1a. So definitely, which ray will undergo more deviation? So definitely the violet will undergo more deviation because the mu for violet will be more than that of the yellow or red. So therefore the deviation suffered by the violet will be more than that of the red. So that's why the violet color in the spectrum, the violet will have more deviation than the red. We'll write it here. Deviation for violet, deviation for yellow, deviation for red. So based on this, like this we defined the deviation. So now is it spectrum okay? So let me bring the basic diagram. No. So if a white light is incident, when a white light is incident, it will break up into its constituents. I do have colors. Violet, this will be, this will be yellow, this will be red, and this will be the undeviated ray. Now we'll compare the deviation. So this is the incident white light. This is a mu small angle prism. So the deviation suffered by, this will be red, yellow, this is violet. Okay, now, so violet, yellow, red color light here. So this particular thing is what we obtain here as spectrum. This I'm showing in some image. So like this is what the textbook diagrams will be there for you. That one. So why the violet will have more deviation than the red? This is a basic formula. Now this particular dispersion, how to study this dispersion? So first we'll define a quantity called as a angular dispersion. There's a difference in deviation. The angular dispersion, we'll use some symbol. File values. Okay, this one. The difference in deviation suffered by the violet color ray of light and the red color ray. The difference of the deviation is what we'll call this as angular dispersion. So this will become mu v minus 1 into a. Okay, mu v minus mu r into a, that one. So this will be the dispersion. So now we'll define one more quantity to study the we have one more definition for this. It is also defined as, we have one more definition, angular dispersion, rate of change of angle of deviation with wavelength. Angular dispersion, it is also defined as rate of change of angle of deviation with wavelength. So this will be d of delta by d lambda. Like this, we define the angular dispersion. Next, we have one more, dispersive power. This is defined as ratio between angular dispersion to the mean deviation produced by this one. First, we'll define this one. It's a ratio of angular dispersion to the mean deviation. So dispersive power usually will take this one. So phi by mean deviation delta y. So the deviation suffered by yellow color ray of light is called as a mean deviation. So we'll give one specific name. This is called as a mean deviation. The deviation suffered by the yellow color ray of light is called as a mean deviation. Of course, yellow is not the middle of the spectrum. Green will be the middle of spectrum. But we are not talking about the physical position in terms of the wavelength. The deviation suffered by the yellow color light will be the deviation of the spectrum. How to measure the deviation of the dispersed light? The deviation suffered by yellow color light will be the reference for the spectrum, that one. So if I ask you, what is the deviation of the resultant spectrum? So what deviation suffered by yellow color light, that should be the taken as reference here. So now this should become equal to mu v delta v mu v minus mu r by mu I minus 1 into. Okay, this is the expression for the dispersive power. So what is actually, so the omega will tell us the, so what is mu v minus mu r? So this will give us some sort of like a, the quality of spectrum. The quality of spectrum depends upon the dispersive power. Greater the dispersive power means the given prism is able to split up the chromatic light like a more orderly into its constituents. So the quality of spectrum depends upon the value of omega. Greater the value of omega, quality of better the quality of spectrum. What do you mean by quality of spectrum? Distinct. If you are able to identify the colors separately, individually, no mixing of that one, then the spectrum is called as a distinct. That one, clear and distinct spectrum, what we can call. Hmm. The quality of spectrum depends upon the higher value of omega. So therefore, if you want to break up a white light into its colors perfectly, then you should prefer a prism which will have higher dispersive power. This is a background. This is nothing but the difference in the refractive index for the violet and red. The dispersive power depends upon the difference in refractive index for the violet and red, that one. So uh, we can define like dispersion per unit deviation. So what is the basic how you can, we can also write it as dispersion per unit deviation. So usually this mu I, where all references, then we can approximate this one. Can be used in numericals, in problems. So the refractive index of material for yellow color wavelength is available just if you take the average of refractive index for, if you take the average of refractive index for the violet and red of the given material. Means you want to know the refractive index of this given material for yellow color light here. Then if you know the refractive index of material for violet and red, if you take the average of that, you will get the refractive index of the material for the yellow color light. If you know the mu and if you know angle of prism, then you are able to calculate the mean deviation. So they need not to mention mu y. If they give mu v, mu r, from that you can calculate the mu y. Okay, this is about the splitting up of white light into its colors is what we'll call dispersion. Again, the spectrum will be pure, impure spectrum. Two types are there. Pure spectrum means where the colors will be distinct and there'll be, all the colors will have the appreciable brightness here. That's called like a pure spectrum. For a pure spectrum to obtain, the dispersive power should be very high. If it is some 3 or 4, yes, you'll get a good spectrum. If the omega is around say between 1 and 1.5, then the spectrum obtained will be impure. There will be overlapping of colors and the intensity of colors will be not high, will be very low. That's called like a impure spectrum, what we say. Hmm? So first we started with the Cauchy's equation. So Cauchy's equation, what it tells that the mu of material depends upon the wavelength. Then from there, so when a white light passes through a prism, the different wavelengths here will have the different deviations. So that particular thing is what I have just insisted here. The deviation suffered by violet will be more than that of yellow and red, because mu v refractive index of the material for the violet will be more than that of the yellow and will be that of the red here. So therefore the violet will suffer more deviation than the red or yellow. Then the difference in deviation suffered by the violet and red is what? The angular dispersion. And the deviation suffered by the yellow color light is what? The deviation suffered by the white light. So this is called like a mean deviation. Then we define the dispersive power. Dispersion per unit deviation. Okay, like this is some theoretical background is what we have set up here. Now, where the spectrum will spread more at violet, the spread will be more at violet than at the the prism spectrum is spread out more at violet and than at red and here. So this I'll explain how it is possible. The prism spectrum. How it is possible? We know angular dispersion, how we define. So let me divide and multiply d mu. Listen. So now next we have the formula for deviation for small angle prisms. Then Cauchy's equation, what it tells, a plus b by lambda square. So let me bring this one. So the first d, I'll differentiate this equation. Solving this will end up with 2ba lambda cube. So you look at the where the dispersion is more, we know lambda for violet will be less than that of red. So therefore the dispersion means spread. What do you mean by dispersion? Spread of colors. So therefore where the dispersion for violet will be more than that of the red. So hence what we can conclude here now, the spectrum is spread more at violet than at red. You look at the spread here. So definitely it will be more at lambda for violet will be less compared to red, no? So therefore the spread will be more at violet than at the red. The spreading will be more at, of course, the violet will spread more. Again, the spreading at violet will be more. So we are not understanding this. So what I mean to say is here, if a white light is sent here, we'll get a violet here. The violet itself will spread more. Spreading will be more. Means, okay, so here this spread will be more. Huh? If I draw the thick line, may not be important for us. This spread will be more at violet, then the spectrum will spread more at violet than at the red. This may not be important, just some statement was needed. Okay, this about the some theoretical background, what we have brought it here. So next we'll go for the application part of this one. First, deviation without dispersion. Okay. I'll take the two achromatic combination of prisms. Later on, I'll bring it. No. So what is our topic will be? Deviation without dispersion. What do you mean by deviation without dispersion? So I'll take two different types of prisms. This is A dash. This will be mu dash. So this will be the crown prism. This will be flint. Crown glass flint. The refractive index of the material will be slightly different. Suppose a mu for crown 1.57. For flint it will be 1.59. Slight difference in the refractive index of the two materials. I'll make them prism of different some small angles. Again, we are discussing small angle prisms. So this is called like a combination. So I want deviation without any dispersion. Means when a light passes through a prism, it will spread. But what I want the white light to pass through the prisms. Let it undergo deviation, but there should not be dispersion. So for that, I'll take the combination of prisms here. So let's go for the ray diagram. I'll decrease the thickness of them. So when a white light is incident, so first the red, then this will be the violet, I'll choose some other color because prism I have to show yellow color light. No? Yeah, fine. Okay, this will be the flint glass prism, crown glass prism. Okay, there's a flint, refractive index be mu dash, angle of prism that would be A dash. The violet, also will undergo deviation. And finally, we'll get back the, if you see these two, there is a deviation. The deviation suffered by the yellow color light is what? So there's a white light, so no question of that one. So what was the incident? Incident white light. Emergent white light. Sir, why you are not showing yellow color light? Of course, yes, you can take the yellow. There will be yellow also. So this will be red, violet. This will be yellow. Okay, there's a deviation. So there's the incident light. If you look at the incident and emergent light, they're not parallel, so there's a deviation. But the incident light was white light, and the emergent light was the white light here. So therefore, there is no dispersion, but there's a deviation. Okay, let's discuss this particular condition. What should be the net angular if there should not be any angular dispersion. Net angular dispersion. Plus we'll take it. So this should be 0. This should be mu v minus mu r into a. So therefore, this a dash is equal to minus of mu v minus mu r a bar some formula I obtained here. So for combination for achromatism, what we call achromatism. So this called like a achromatic combination. Achromatic means I should not get any colors here. Condition for chromatism means there will be color. Achromatism means there should not be any color in the emergent ray, that one. So it has to satisfy this basic idea. For achromatism, so if you don't want any like a spreading of light, splitting up of chromatic light, no, so then it has to satisfy this condition. Okay, let's calculate the expression for deviation. What about the dispersive powers? How they'll be related to this? Okay, now I'll bring one more condition. How dispersive powers and deviations are related. Huh? So from this equation, we know mu v minus mu r. Let me adjust mu y minus 1. mu I dash. So this mu I minus 1. This will be deviation for the omega delta dash omega dash. Sir, how you are writing directly? Mu I minus 1 into a. I'll write one more step. I'll write one more step. Can you write this A here? Can you write this A here? So what is this quantity? What about this quantity? This will be angular dispersion by mean deviation will become dispersive force. And this is the mean deviation for the crown prism, mean deviation for the flint prism. So therefore this will become delta mean deviation. The deviations is called as mean deviation omega delta dash omega dash. So like this now we will get a some basic equation dispersive power omega by omega dash equal to delta dash by delta. If omega dash greater than omega, then A should be greater than A dash. Depending upon how you want conditions, no, you can bring it here. Okay, after this we'll go for the net deviation. So the net deviation is given by the net deviation delta net is equal to plus mu dash minus 1 into A dash. Later on I'll bring that some image. Now you see this. Further we'll explore this equation. Mu minus 1. So shall we adjust mu minus 1 a, let me take common. Mu minus 1 a will be common 1 plus then I'll adjust one more mu v minus, okay, this will be mu minus 1 a dash, we have derived expression for a dash, no? Some, yeah, substituting this equation there, 1 plus mu dash minus 1 by mu minus 1 a dash by a, I can also write it as there's the equation a dash by a, I'm replacing from here a dash by a, what we can write mu v minus mu r by mu v dash minus mu r dash. Now we will readjust these things. 1 minus mu v minus mu r by mu minus 1 into what is mu v minus mu r? So this should be the dispersive power. And this quantity will be deviation. The net deviation given by this particular formula. So here we have replaced here. These two quantities are replaced by omega. This quantity, different colors I have to use. This quantity is replaced by omega. This quantity is replaced by omega dash. Okay, fine. So when deviation without dispersion, okay, there's a one basic mathematical formula is what we have obtained. Achromatic combination, this is what we obtained here. Okay, practically, let me show some image which I took from other sources. Hope everyone is able to see the complete description. Yeah, this is our basic discussion. So now, if a white light is passing through it, it will spread in the first prism. Okay, again the spectrum will undergo deviation. Then again here what means the second prism will recombine light. So recombine white light is what the emergent light again will be white light only. I don't get any spectrum. White light is incident, again I'll get back the white light. So therefore we don't have any dispersion. But if you look at these two, there is a deviation. What is that net deviation? We have this one. So if you extend this line, so these two, the incident and recombined white light, they'll not be parallel. And what is that deviation suffered given by this particular formula? This is a condition for achromatism. For this to happen, the mu of a material for the violet and red, and the angle of prism should be related in this way. Okay, so I think do remember this will be very very important equation. If you know formula, because in exam you can't derive, you are supposed to remember this. Net deviation. Already I wrote it here. Different books they are given different method. Okay, we can just the basic formulas are very important. How the deviation without dispersion, how the dispersive powers and the deviations are related. There's a formula. Net deviation, there's a formula. Condition for achromatism, there's a formula. I think there's three formulas. Please try to remember and just underline. Okay, we'll go for dispersion without deviation. This will be our the next topic which we have to discuss here. So I'm going to pick up a dispersion without deviation. So let me take the combination of prisms. Strictly, what is the condition? There should be deviation, dispersion without deviation. White light will be incident. I should get a color finally. Let's take the, so there's a white light is incident. Just we'll keep the reference one. Dispersion without deviation. I should draw them carefully. Wallet will split up. Right. Combined. Wallet. Then the you can clearly see there is the yellow color light and the incident white light. So this is the incident white light, wallet yellow red, wallet yellow red. So this is A dash mu mu dash. So there's a crown, there's a flint glass. We have to bring all again the same thing. So here we do get spectrum. Emergent spectrum, but dispersion without deviation. Oh, I think I'll draw it properly. These two should be parallel. Then there's no deviation. So what is the basic idea now? So the combination should not produce. The combination will not produce any deviation. It should be 0. All these are small angles. So finally again A dash is equal to there's a condition for no deviation. What do you mean by negative sign? They should be measured, they should be placed in opposite sense. What do you mean by negative sign? The two prisms should be placed in such a position. You can see that this will be inverted and the bases will be inverted. There's a meaning of this negative sign. There's a condition, the combination will not produce any deviation, so the net deviation is 0. So then it should satisfy here. So now net will calculate the net angular dispersion. Net angular dispersion. So what is the basic formula for this? Deviation let me take A common, mu v minus mu r. A dash by A. Let me adjust one. Mu minus 1, I'll adjust here. sorry. There's just some calculation. Oh, yeah. Again, same thing. So I will take help of this A dash. Shall I bring this? Why this value? Again, it is understood for yellow only. So this will become mu V dash minus mu R dash. A dash by A will be minus 1 mu minus 1, let me take common. There's a deviation. Okay, there's a net expression for the dispersion. Okay, so these are the some theoretical small idea. Dispersion without deviation, deviation without dispersion. Whatever omega omega dash, they are the dispersive power for these prisms. Omega omega dash. So the net dispersion depends upon the deviation produced by the crown prism, then the dispersive powers of crown minus this particular thing. So if you want more dispersion, if omega greater than omega dash, will have a dispersion. Suppose if omega less than omega dash, the order of color violet will be above the red, or that one, that depends upon this sign. If there is a positive, violet will be below the red. If it is a negative, the violet will be above the red. The sign of this also will give us the order. If the violet is below the red, this will be positive, net dispersion. If violet is above the red, then the net dispersion will be negative. We can, sir, how you can say it? It may happen like this, sir. It may happen. I will show it here. It may happen that red right, and this will be violet. So there's all possibility. So there's nothing that violet should be above the red. No, it is also possible. Of course, they're not parallel. And the yellow color will be parallel to this one. So here you can see this. This will be A, A dash, mu, mu dash. Okay, fine. It is also possible. Okay, one more last we have. We'll go for one more. So there's all possibility that there will be dispersion, there will be deviation. This will be very troublesome for students. we can have a prism combination in such a way that there's a white light is incident, it will break up red, 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 violet, violet, violet. Then if you see the yellow, so here there's another combination a dash mu mu dash. There's a white light. You look at these two; they are not parallel. I will further these two. So here, what is the combination here? Hmm? Dispersion and deviation both are non-zero. Both dispersion and deviation are non-zero. So net will be delta plus delta dash. This will be both will be non-zero here. It can happen. Are you getting no? So in the combination of prisms, deviation will be zero, dispersion will be zero, or both will be non-zero. It is widely used in plenty of applications. Now, we'll directly take the glass slab, what actually happens, because this is something very important for us. If we take a glass slab, what is a glass slab? We can assume it made up of two prisms. Fine, this is one angle. Glass slab. And there's another angle. If a white light is incident, what will happen to the white light? Incident white light. No deviation, no dispersion. What we know, no deviation, no dispersion. Am I right? There's a one reference line. Let me draw it. So when a white light is incident on a glass slab, what actually happens here? So the red color light will break up. Then the violet. Let me draw the diagram properly. It will be easy. Then this will be the yellow. And that yellow will be parallel. Emergent. Oh, it should be black only. Yeah, this is the emergent white light. Incident white light, and there's a glass slab. Hmm? So when a white light is incident on a glass slab, no deviation, no dispersion. No deviation and no dispersion. Because we can just assume this is like a crown and flint, no? So these two angles will be equal. So therefore the net deviation, net dispersion will be zero, and the emergent light will be parallel to the incident white light. So therefore there's no deviation. These two are parallel. And we don't see any colors. So no dispersion. And the emergent white light is parallel to incident light, so no deviation. So what is our question like? When a white light incident on glass slab, what will happen? No dispersion, no deviation. What is the answer? Okay, these are the things what you must know. So these are all some theoretical background. So almost I think I covered the complete the theory part which is required for the solving of the prism problems. In the coming class, I'll come with the different types of numericals. Hmm. Okay, kids, we'll meet in the next class. Thank you, all of you. Yeah, kids, we had one more theoretical topic today we have discussed here, where we had the, let me add this. Oh, yeah. We discussed the prism, the dispersion concept. So when a white light is incident on some prism, so the prism, what it do, it will split up that white light into its constituent. That is called like a dispersion. Then we defined the angular dispersion, the deviation suffered by the wall, the difference in deviation suffered by the violet and red are called the difference of the difference between the deviation suffered by violet and red is called as a angular dispersion. Then what is the mean deviation? The deviation suffered by yellow color light is called as the mean deviation. Then we define the dispersive power. The ratio of angular dispersion to the mean deviation is called as the dispersive power. What do you mean by dispersive power? Like how powerful is the given prism in splitting up of white light into the different colors. The measure of that is what? The dispersive power. Then I brought a situation where deviation without dispersion, dispersion without deviation. Then we can have a situation where both dispersion deviation will be non-zero. Then we have a situation where both will be zero. All possibilities are there. Deviation without dispersion, dispersion without deviation, both will be non-zero, both will be zero. Both will be zero in case of a glass slab. I think this completes your total prism theory. Coming class, let me focus on the numerical, different types of numericals. We directly take it because almost we know the total theory now. Okay, yeah. Thank you all of you. Take care. Bye. See you.